Continue now for the last hour of today. So we talked about MPI send and MPI receive, and then this function MPI send receive. These two exercises, exercise 7, exercise 8, try to demonstrate how to use these functions. Starting from exercise 7 here, I'm starting from slide 46, the slide with the number 46 down here. So in exercise 7, you will find this data.txt. This is the same file as exercise 4. So 8, that's 8 lines. That's our favorite data.txt by now. And what we want to do is, as always, all elements are read by the root process. And then the elements are scattered, one to each process. And they are stored now in this variable var0. So this is very similar to what we've been doing since exercise 4. Okay, what we want to do now, though, is to call MPI send and MPI receive such that all processes with even ranks store in their variable var1 the value of variable var0 corresponding to the next odd rank, and all processes with odd ranks store in var1 the value of var0 corresponding to the previous even rank. So let's just make this a bit clearer with a picture. So starting from the beginning, you have your data.txt file. And we call, as I said, read lines again, like we did so far, and these go on rank 0 into this 8-element array. And each process now has 2 additional variables, var0, var1, var0, var1. These are the ranks. These are representing the ranks. And so what we first do is something we know how to do so far, right? It's MPI scatter. So that each element here of the array ends up in var0 of the 8 processes. So far, so good. Nothing new here so far. But what we want now is to group these ranks in pairs, and even and an odd one. So 0 with 1, 2 with 3, 4 with 5, 6 with 7. And what we want is, in the first step, the even ranks call an MPI send, so that their var0 ends up in var1 of the next odd rank, right? So the even ranks call MPI send, and the odd ranks call MPI receive. So then that's what that should look like when the communication completes. So this red here represents the value of var0, and it should be copied to var1 of the next rank. var0 of process 2 should be copied in var1 of process 3, etc. So you see that this communication has happened. And then in the next step, what we want is the opposite to happen. So the odd ranks should send their var0 to var1 of the previous even rank. So in the end, you should end up with something looking like this. You have pairs 0, 1, 2, 3, and they have copied the neighboring value of the variable. Okay. So the to-dos that you have to do is complete the MPI send and MPI receive. So there are 2 of these. So you see at the beginning, we say if rank modulo 2 is 0, meaning if rank is an even valued rank, then do an MPI send otherwise. So the otherwise means rank mod 2 is 1, and then do an MPI receive. And then you do the opposite, where the odd ranks send and the even ranks receive. Okay, and if you do it correctly, then you should, in your x07 output.txt, see something like this, where you see that this. Okay, so these are the values of. These are just the values that you scattered. So there's nothing special about these 8 values, but what you should have achieved is that this value is now in var1 of the next rank, And then this value, this odd ranked process has copied this number into var1 of the previous even rank, right? So if you draw like x's, then these values should match if you've done it correctly. Right. So yeah. So that's the task. Let me. Yeah. So let me open the exercise. Again, everything here looks familiar. The scatter operation has been completed for you. And what you need to do is complete these lines here, these 4 to-dos. Okay, so why don't you do that? And we come back at 15, in about 9 minutes, 15 past 3, to do the solution. You have any questions? Don't be shy. So I should maybe mention again that if you look into the script, right? So basically, your job is restricted to running for just I think that's 1 minute, yeah, 1 minute. Actually, the job should take much less than 1 minute. So if you actually see it running out of wall time, then probably you've done something incorrectly and your program is stuck in either sending or receiving. So that should be an indication to you. If it takes more than 10 seconds to run, it should be an indication to you that something is wrong. Okay. So let's go through this step by step. So var 0 is already filled. And so the first thing we want to do is when the even sites call MPI send, I want to go back to my picture. Yes, so this is the step that we want to complete first. So where's it? Oh, there it is. And then we first write the MPI send. So just let's see what the arguments are. So first is what I want to send, so the send buffer. And this, what I want to send is var 0. And then it's the count, so 1 MPI double. Okay, and then the destination. So this is rank 0 will come in here, rank 2 will come in here, rank 4, and rank 6 will come in here. And I want rank 0 to send to rank 1, rank 2 to send to rank 3, etc. So the destination is rank +1, right? And the tag, I'll just use any tag here, 0, doesn't matter, because it's only one message. Good. Okay, now, if I'm not an even site, then I am an odd site, and I need to call MPI receive. So this MPI receive will be called by process 1, process 3, process 5, and process 7. And what is the first argument? The first argument is the receive buffer. So where I want the data to go, and this is bar 1. It's one MPI double element, double. Okay, and then what the next argument is the source. So where is this message coming from? So if I'm process 1, then this message should be coming from process 0. If I'm process 3, it should be coming from process 2, etc. So what do I put here? Rank -1. I don't care about the tag. I could put 0 there, but I can also just put any tag. That will be equivalent. The communicator and status ignore. Okay. Right. So what I've done now is just half of this process, right? So once that finishes, then I will be in this state. I also want to do this bit, right, where the odd sites now send to the even. And that's done here. So if I am an odd site, right, then I want to do what? Well, I still need to send my bar 0. Double. But now, where am I going to send it? So if I'm process 1, I need to send to process 0. If I'm 3 to 2, etc. So now the destination is rank -1. And everything else is the same. And so if I'm not odd, right, then I'm an even site. So I'm 0, 2, 4, 6. And where do I want to put it? Into bar 1. It's one element of type MPI double. And what is the source of this message? Well, it's my next odd rank, so rank +1. MPI any tag, MPI com world, MPI status ignore. Good. So hopefully, in this batch 7 and it's done. See, took 2 seconds. Well, let's see if it's correct first. So X07. Okay, what do we have here? So this is all in a random order again. I just want to sort it so that I can try and compare a bit. So this first column here with var 0 should just be the elements of data.txt. Let's just confirm it. Indeed, it's the elements of data.txt. Let me just do this again. And now this one should be the same as this one, and it is. And this one should be the same as that one, and it is. The same should be true for this pair. The same should be true for this pair. And the same should be true for this pair. Good. And so, any questions concerning this? No? Okay, I'll continue on then to the next exercise.
What about the tags? Why did it not care?
Because just one message is going to each process, right? So it's not like we're sent. I mean, we could have put 0 there. We could have put 0 here and 0 here.
Okay.
I mean, there's only one message going to each rank. So there's no ambiguity of which tag should be. There's no ambiguity that we would like to disambiguate by picking a tag. That's all.
Thanks.
Okay, so yeah. So exercise 8 demonstrates the use of an MPI send receive. We're reading the same file, data.txt, with the 8 elements, just as before. And again, the elements are read by the root process, and then they are scattered to all processes as before. Yes, but what is the catch here is that now we have 3 variables. One variable is this varproc. That's the element received from the scatter operation. But then we have another variable var next, which is meant to contain varproc of the next process. And we have varprev, which stands for previous, which is to contain varproc of the previous process. And for this, we want to use an MPI send receive. And let me just, again, try to draw this in the same way I did before. So starting from the beginning again, we have data.txt. The elements are scattered to the 8 ranks. We haven't scattered yet. So the rank 0 reads the 8 elements in this array, and now the elements are scattered to this varproc of each rank, right? And so when the scatter operation finishes, we have something like this. Good. So the first thing we want to do is every process should send varproc to the next process so that it goes into the next processes of our previous, okay? So you do an operation like this, and actually we want this to be periodic. We want the last process to send up to process 0. So you need to figure out a way to do this in a smart way, so that when this communication finishes, this looks a bit like this. So you see red goes with red, green goes with green, this cyan goes with cyan, yellow with yellow, purple with purple, some other blue with blue, etc. Okay, and then the other thing we want to do is do the same thing, but backwards, right? So you want each process to send to the previous process and put that in that previous process's var next. Something like this. So again, all processes need to call a send receive. Yes, all of them. So you can't do it like before when you have if, your order, if you're even. We want to do it with 2 send receives without any if statements. And then you end up with something like this. So in the file, if you look at the file, there is basically just 2 send receives which are empty and which you need to fill the arguments of so that you achieve what was in the previous picture. When you do that, then you can cap the output and sort it. And if you did it correctly, first of all, you should see in this first column here the elements of the file. So because that's just the elements that have been scattered. And then var previous should just be, starting from this one, right? It should just match the previous one. This one should match that one. This one should match that one. And if you go down to the end here, this one should match that one. And then this one should be periodic, so it should match the last one. This one should match this one. Good. Var next should match this one. So this second one should match this third one, right? So, and this one should match that one, if you did it correctly. Okay, so so I'll leave this picture here. And right, so why don't we do this in the next 10 minutes and come back at 35 past. Sorry, I missed the time. Yeah. Right, so the send receive. So let's begin with the first one. Just a moment, let me gather. And okay, so first I will go back to, so yes, so this is what we want to do first. So send forward into var previous. MPI send receive. Let's see the order of these arguments. So first is the send buffer. So what do we want to send? We want to send var proc one element MPI double. Now, where do we want to send it? We want to send it forward, so we want to send it to the next rank. So the destination should be rank +1. Now there's a trick here, because if this is the last rank, we want this to be 0. We want this to evaluate to 0. Everything else, it's okay if it's just rank +1. So one way to do this is do a modulo with nproc, okay? So as long as rank is smaller than nproc -1, then this evaluates just to rank +1. When rank is nproc -1, then this evaluates to 0, as it should. Right, so the tag is 0, and then the arguments for the receiving side begin. So where do we want to put it? We said we want to store it in var previous. One element, MPI double. And now we want to set the source. So where is this coming from? So this is coming from the previous rank. So this should be rank -1. And this -1 is okay as long as this rank is not 0. If it is 0, then this will become -1, and there is no rank with rank. There is no process with rank -1. So what we need to do is some arithmetic here. So maybe need to take a minute to look at this, but this indeed evaluates to 0 when, evaluates to nproc -1 when rank is 0, as we want it to be. We don't care about the tag, right? And this is the communicator, and MPI status ignore. Good. So what we've achieved now is this communication, and now we want to do the next send receive, which is that communication. Good, let's go. So var proc 1 MPI double. So the send is the same, but now it's the inverse, right? So this is now going to be sent backwards. So I'm just going to copy this. So I send backwards now. The tag is 0. Good. And then I want to store it in this var next. This is not fubble. This should be double. Right. And where is this message going to come from? It's going to come from the next process. And I can use this modulo operation to ensure that this becomes 0 when it's the last rank. MPI any tag. And I'll just copy this. So it's going to be the same. Good. This should now compile. And hopefully I should see the result as expected. All right, so let's see. So this is just the elements. Let's sort it. These are just the elements. This column is just the elements in the file, data.txt. And now previous should match that one. This one should match that one. This one should match that one. Good. And then next should match the variable of the next rank. Okay, good. So any questions here?
You use the tag 0 twice for each rank. Is that okay?
Yeah, but for different but first of all, this will complete before you go to that one. Mm-hmm. So it's not like you have two messages in flight with the same tag, which is fine. And the other thing is that the receiver is different for each tag. So it won't, it won't conflict in any case, because the tag is to disambiguate messages which have the same sender and receiver.
Okay, so the pair, it's unique for each pair.
Yeah.
Thanks.
Okay. Okay, so we have 20 minutes left, and I'll use this to talk a bit about hybrid. So combining this with OpenMP. So I assume you did some OpenMP in the first lesson, and I just want to talk a bit about how one would go about. Where do I have it? Oh no, I have it at the end. Excuse me. So after exercise 8 is a short introduction. So we don't have much time maybe to see the exercises, although you can try them yourselves offline. Let me just introduce some concepts. So combining OpenMP and MPI. So things that you can do this is, for example, using OpenMP parallelism within a node and MPI parallelism between nodes. So why do you want to do this? You could get better control of granularity. It might be easier to parallelize across domains that are not exactly divisible by the number of processes available, because OpenMP sort of dynamically allocates tasks to processes, whereas MPI, you need to be a bit more deliberate about what each process does. And it also allows for controlling parallelism in less parallelizable regions, such as I/O. For example, if you have, I don't know, nodes with a lot of processes, right? With a lot of cores, then it might be inefficient to do reading and writing in parallel of files with that many cores. So an example use case would be to use OpenMP inside the node to parallelize compute-intensive operations, but then when you read files and write files, you use one MPI process per node without any threading, and that might be, for example, faster. Anyway, there's several reasons why you would like to combine. I just try to give some examples here. So there are several types of this hybrid parallelism, but the simplest case is what we will talk about here. I just want to say that that in the most common case, you have a situation in which only one thread calls MPI. So you do not call MPI within OpenMP parallel regions. Or you might call MPI within a master OpenMP region. So master OpenMP regions are regions where only one process goes through. Another mode of operation, so this is the opposite of the first bullet point, is any thread calls MPI. And then you might have two kinds of modes. You could have a serialized mode in which multiple OpenMP threads call MPI, but there is a mechanism to serialize the calls, so they're not done in parallel or concurrently. So you had MPI thread safe library, which allows concurrently calling MPI. So these are much more complicated and much more difficult to debug situations. Usually what you have is something like this, where only one process calls MPI, one OpenMP process calls MPI. So thread awareness is MPI is basically done by calling MPI in its thread rather than MPI init. And all this does is the same as MPI init. It's just that this function will return to you what kind of capability this implementation of MPI allows. So if it returns this constant inside provided MPI thread single, it means that there's no thread safety assumed, and this is equivalent to MPI init. And then there are these other three options, which mean that this implementation of MPI is capable to run one thread calling MPI, or multiple threads as long as they're serialized, or multiple threads, meaning that any thread can call MPI. So here we will just cover using single mode, where parallel regions can exist in a program, but MPI is just called outside of the parallel regions. So in example 9, we don't really have enough time to look at it, but there's not really much to do. It's just the same as the first exercise for MPI, but you're also calling OMP get number threads and OMP get thread number in each region, just to see how it works when you include OpenMP and MPI. So basically, you should look a bit into the sub 9 and look at it about how that works. So each MPI process spawns its own OpenMP region, and yeah, and basically there is a hierarchy in which MPI processes are at the top level, and then OpenMP threads are spawned by the process. So you should imagine using this hybrid mode as something like this. So in this mini example, in this cartoon, I am using 4 OpenMP threads, and I'm calling MPI run -n3. So these are the 3 parallel instances of my hybrid program, each one running on a node. And then they go, and then when they hit one of these Pragma OMP parallel regions, what I have is this one MPI process spawning 4 threads, and then doing something here like a parallel for loop. And then when the region ends, then you have one MPI process again. And then when you hit another parallel region, OMP parallel region, you again split into 4 threads, etc. So example 9, just I'm just going to outline a bit what it does. All it does is you don't really need to do anything. There's no to-dos here. It's just running it and observing the output. So there is you run it with MPI, and then you go into a parallel region, and then you get the thread ID, the number of threads, and then you have this statement which says this is OpenMP thread integer of number of threads, MPI rank, and number of processes. Okay, and then you can play, if you like, you can play. Oops, yes. You can play with the number of threads here and the number of MPI processes to see how this changes. Okay, and then I have another exercise 10, which unfortunately, due to time, we can't really cover, but again, there's no to-dos there. It's just basically just done for you. But what it does is it implements a dot product using MPI and OpenMP. And what you can do is change how you distribute between MPI process and OpenMP threads and observe a bit the timing. So let me show you what this program looks like. Oops, oh, yeah, what's going on? So there are two files here, x.txt and y.txt in exercise 10. And each one has about 360,360 elements. And so what this program does is, first you have, yes. Okay, so you have your read line. So rank 0 reads x.txt and y.txt, and then scatters elements of x and y to x local and y local. And then each process does the local dot product, right? Dot log, okay? But this is also parallelized with OpenMP. So if we go back to this cartoon here, right? Up until this region, we're just following the single line. And then when you hit this region, then you split up into the OpenMP threads, or however you have defined in this OMP num threads. And that's where you do this multiply that in a thread parallel fashion, okay? So this OpenMP region is just open for this loop. And so when you come to the reduction here, where you want to reduce this local dot product over all processes, then this is done outside of an OpenMP region. So only one thread calls that MPI reduce. And then we come here, and all I'm doing here is I'm opening a parallel region so that I can get the number of threads again and use it in the print statement. That's the only reason I'm opening up this region here. And then you get some info also about the number of milliseconds this took to run. Okay, so if we had a bit more time, I would ask you to compile and run this and then change in the Slurm script the distribution between OpenMP threads and MPI processes. So the way it's set up here now, it's 2 threads, 4 processes per node. So in total, 8 cores are being used, but you can also change this distribution within the, by changing this job script and the parameters here. Okay, I think I'll stop now just to leave about 5 minutes for questions, if you have any. And I hope you enjoyed this introduction to MPI and a bit of hybrid programming.
Thank you, Yannis. Before any questions come in, we would like to know if you enjoyed this this first day of MPI and hybrid programming, as Yannis said. If you can please fill in our feedback form. I've texted the link to the feedback form on Zoom. It's the last link you'll find there, and also on the Slack channel. So your feedback is invaluable to us, and we do take it into account. So please provide us with your feedback. And if you have any questions for Yannis, please unmute yourself and speak up now. Thank you.
So Yannis, could you clarify in saying this diagram that you can see on the screen?
Yeah.
The number of processes, the number of threads,
So
I guess
here the
here
example is,
do we have 3 processes and 4 threads
3
per
MPI processes. Yes, and 4 threads per process. And so MPI stuff happens when we're not in the shaded regions. So MPI stuff should happen when we're not in the shaded regions. And in the shaded regions, you do the compute intensive things like summing the array in the example 10. Whereas outside the OpenMP regions, you call MPI like reduce, the reduction operation, or MPI com rank, MPI com size, MPI com scatter. It's done outside the shaded regions. That's the mode that is most commonly used when you do hybrid programming.
Say in the example where you have to read 2 very large text files for the elements of two vectors,
Yeah.
and take the dot product, you could split it into, I don't know, multiple processes where each of them takes a portion of those elements, and then
Yes,
open. And then you could open a
I don't know.
MP region and do the dot product for
Yes.
each sub vector.
Exactly.
And then you would do this MPI reduce, for example, outside the pragma.
Exactly.
And sum the rest. Okay. Okay.
Mm-hmm.
Thanks.
Yeah. Ideally, you would also read the files in parallel, but that's, I think, for Wednesday to learn about how you do I/O in parallel. So far, I try to restrict the examples to things that we know, which is one process reads the 2 files and then scatters the elements. Okay. It's good to keep in mind that there's also MPI-IO, which allows reading the files also in parallel. Okay, so you don't have one process reading and scattering, but you have all processes reading their chunk. Each reading their own chunk.
And the output, could you show the output, like the last region that you opened, to show the output, just a line of code where you show the output.
Exercise 10.
Can't remember which one it was.
This one.
Yep.
This bit. Yeah.
Okay.
So here I'm just open. Yeah. The only reason I need to do this is because n threads here will only give me the right number of threads if it's in a parallel region. So I have to open a parallel region, create a single parallel region, and then print n threads, so I just get one line. That's the only reason I'm doing that like that.
Okay. nproc is in the diagram before it is 3, right? And in the
yes. Mm-hmm.
and n thread in this case it's 4 in that diagram.
Yeah, it's the diagram. Yeah.
Okay, thanks.
So in that case, in this parallel region, you would have something like 12 cores running in parallel, right? Yeah, 3 times 4, 12, doing this in parallel. It's just like.
Yep. So each.
Right. So yeah. So this cross section here, you have 12 of these running. Yeah.
in the terminology, each rank goes through this script, and then when it hits pragma, it splits into threads.
Yes. And then joins at the end of the scope of the pragma, which is at the end of the for loop.
Mm-hmm.
Then you join and you get back into one thread per process, per MPI process.
So in the SBatch script, the Slurm script.
Yeah.
Because I think there we.
Yeah. So the way it's set up now is 2 OpenMP threads per process, 2 nodes, 4 processes per node. So this is 8 MPI processes, and each one has 2 OpenMP threads. So in the parallel regions, you have in parallel over the whole machine 16 of these running, which is why this end tasks is 16.
Okay.
But you can change that in the script and see if it's fast or slow or whatever.
Okay, yeah. So the product of the processes times the threads needs to equal n tasks.
Yeah.
Okay, thanks. Thank you, I really enjoyed the event today. Thank you.
Oh, thank you.
So if there are no more pressing questions, because maybe Yannis has to get on with other things today, then we will leave it for today. I'm sure Yannis will be at hand to answer any questions. You can contact him.
Yes.
Tomorrow we have Simone being your trainer. He will be all day like Yannis was today for talking to you about Python for HPC. I would like to thank everyone for participating in today's training event and for your feedback. Please provide your feedback and for attending. And most of all, I would like to thank Yannis for his time and for his efforts in providing the training for you. And thank you again, Yannis. And
It was a pleasure.
We start tomorrow at 10 a.m. With Simone. Thank you, everyone, and talk tomorrow.
Thank you. Bye-bye.
Goodbye.
Thank you. Bye.
Thank you, bye.